Jupiter is the largest planet in our solar system, and it is a gas giant. There is no surface or terrain or terrestrial land mass for any sort of life form to exist or thrive on. It is a mostly gaseous fluid like supercritical fluid like substance that makes up the planet. It is very similar in many regards to the sun, in fact, which makes it a unique candidate to investigate and analyze for the possibility of life. And some would suspect that it is a low probability of life existing there, and that's what we aim to break down in this video. In addition, I've updated or refined my methodology or formula for estimating the probability of life on different planets, or estimating the habitability of a planet. And you should check that out. It's going to be at the end of this video, so stick around to see how I updated it. And I will continue to refine it, create more and more iterations until I am satisfied that it is a really good formula. In addition, we are going to take a bottom-up approach to understanding how life might arise on Jupiter and estimating the different quantities using data from the various different missions that have explored Jupiter already. And that includes the Juno mission, which is the current operating orbiter around Jupiter, and it is the most distant orbiter we have surveying a planet, which is really cool. And it has plans to actually see some of the moons as well of Jupiter, including Io, Europa, and maybe Ganymede. And so that's going to be one of our data points. In addition, we have data from Voyager 1, Cassini, and I'm forgetting one, Galileo. These are the main missions and data gathering instruments we are going to use to inform our perspective. So without further prefacing, let's jump right into it. And so, given the bottom-up approach we are taking, we are focused on understanding the core of the planet, which there has been two hypotheses proposed for what the core is made up of, whether it's a dense rocky center similar to Earth, or if it's more of a fuzzy like dilute substance, fluid like substance that makes up the core. And data from Juno, where gravitational perturbations have suggested indirectly at least that it is a more fuzzy like core that radiates all the way out to about half the radius of the planet. It is made up of heavy metals, dilute heavy metals that aren't much different than the metallic hydrogen that makes up 89% of the planet as we understand it. It is also important to note that a lot of this modeling we have for the planet is indirect. There is not a lot of direct observations that we have because we can't penetrate the uppermost atmosphere of the planet. It becomes difficult to parse through that and directly detect things. So a lot of our modeling is based on theoretical approaches, which can be good and can be, but is not as good as direct observation, of course. So we have this fuzzy-like core that extends about half the radius of the planet, and then we enter the interior, which is made up of metallic hydrogen, where electrons are no longer bound to molecular hydrogen, and they're allowed to freely roam, similar to a conducting metal. So that is an environment that is not conducive to life, given the restriction on the type of molecules available. There's only one, and in metallic hydrogen. And the next portion of the mantle, or the interior, we have the liquid helium along with molecular hydrogen that is in a supercritical fluid state, given that it's above its critical point for temperature and pressure. So you have the supercritical hydrogen and inert helium, both of which are not conducive to any form of life that I could imagine. The thermodynamics would not be in favor of creating any complex chemistry, given the limitation on the chemicals and compounds available, not to mention the extreme environment. So that leaves us with the best candidate, which is the atmosphere. And the atmosphere can be broken down into 3 layers. And one positive point on the atmosphere is that it has a lot of energy input, whether that's through convection, given that the planet is mostly a fluid-like phenomenon. You can have convection take place where temperature from the interior of the planet can move and radiate outward. Not radiate, but convect upward towards the atmosphere. So you're getting an energy input that would be great for catalyzing a life form, including lightning and other electrical input is also available at the atmosphere of Jupiter. Unfortunately, there are only trace amounts, less than 1%, of compounds that aren't helium or hydrogen, and those include ammonia, so a few hydrocarbons, but at the concentration of less than 1%, the diversity is so limited that reactions are likely not taking place that could sustain a complex life form or complex system. And so, even though there's the energy input from both sun radiation and convection and lightning, it is not enough to overcome the limited concentration of molecules to react. In addition, the physical environment is extremely intense and violent, including the winds, lots of storms, and again, the life form would have to be able to suspend itself in an aerial fashion within the atmosphere. And so it would have to remain less dense, which is okay, as long as it doesn't grow to be more dense and sink to greater and greater depth. So overall, there's no great polar solvent or medium for life to exist. Like, we have water as our medium on Earth. I don't like to make a lot of comparisons to Earth because I want to remain imaginative in thinking about life, but there's no polarity in hydrogen or in inert helium, so the medium that is making up that planet is not conducive for promoting any sort of diverse reaction or complex reaction chemistry. And so the thermodynamics are not in favor of producing a system that could sustain life. And so while there is an energy source, we can make the claim that life is not super likely on Jupiter. So with that, why don't we put together for you guys the formula that I will be using going forward and will be refining with time. And that is this one, which I'm putting up on the screen here. We are inputting our probability for various different variables, including temperature, pressure, geological activity, chemistry, and the physical environment, which is similar to what we were doing previously, but now we are weighting the various different variables because temperature and pressure have a significantly greater impact on whether life could exist there. For example, at a very, very, very high temperature, extreme temperature, the prospects for life almost becomes zero, whereas you could have no geological activity, and while that's hurtful and that it is a penalty towards creating a system, it's not as crucial as maybe temperature would be, or pressure. Chemical composition is also really important, and then the physical environment plays a role somewhat important. And so I've weighted all of these variables accordingly, and so then we can input our probabilities and take the product, and we estimate that Jupiter has a 5.6 times 10 to the negative 4, or 0.056% chance of hosting some sort of life form or biological system. And in comparison to our other candidates using our new methodology, we have Mars at 0.38% and Venus taking the lead at 1.2%, given the new, more rigorous method for computing habitability. So Venus has now usurped Mars, and both Mars and Venus have a better chance, according to my estimating, for having life. And so that is where we'll leave Jupiter before we go and explore the moons. And we'll see you there.